today we will discuss the economizer and also we gave some background details here. The economizer is generally be used to preheat the water before it enters into the boiler evaporator. This economizer makes the water, that means the exit condition of the economizer is equivalent to the saturation condition. As you know well that this part is the economizer, this part is the economizer. So, therefore, the water enters into the economizer in a compressed liquid condition and goes to the saturation condition. So, at that pressure. So, the important thing here is this is the lowest temperature points, because you have to extract the maximum heat from the flue gas here, then increase the temperature of the water. So, therefore, it is an heat exchanger here, because the flue gas is passing through this. It is a counterflow heat exchanger, where the gases are at higher temperature and the water is at low temperature, but the specific heat of gases are very low as compared to the water. So, therefore, if you look at any heat exchanger here, the surface areas, if this is the tube and other side heat is applied and liquid is passing through this, what happens here is the surface area outer side, because same amount of heat needs to be transferred to the working fluid. So, the outside area should be higher than that of the inside area, because of the higher lower heat transfer coefficient as well as the surface areas. So, that is why most often it is used. How do we increase surface? Because attaching the fins to that. So, therefore, the fin type of heat exchanger is used, and it is placed between superheater and reheater and air preheater, and it is made of generally vertical sections, continuous tubes. It will be like this. As I mentioned, the fluid goes into this here, you can see like that, but the outside you have a finned tube, because the heat is transferred by the fluid here, exhaust gas goes like that. So, typical economizer looks like this. These are the fin tubes, and the exhaust gas enters here and leaves from the top, okay, and feed water enters from the top and goes back at the bottom. So, it is a counterflow. The flue gas is this side and the water is the other side. Only the difference is the water side is a tube, plain tube, whereas outside is a like fin tube. This is the one generally be economizer, this thing. So, again I am not discussing, it is a similar to heat exchanger, any heat exchanger. So, this is a gas to liquid heat exchanger. The another important thing is air preheater. Air needs to be admitted into the combustion, that is a furnace, at higher temperature than the ambient, because if you supply air directly from the atmosphere, what happens is it is very cold. So, the combustion efficiency is reduces. So, we have to increase, in order to increase the combustion efficiency, you need to send air preheater, or air should be preheated and admitted. So, it receives temperature in a 600 to 800 Fahrenheit. You can convert this into degree Celsius. Okay. I have given deliberately this here, convert into degree Celsius. So, here this air preheater is an important device. Why? Because the flue gas temperature should not be less than the acid dew point temperature. That is why the flue gas gets cooled up to these temperatures, and because it is important, as I mentioned, that the air cannot be air which enters into the furnace should not be very high, otherwise there is a possibility of pre-ignition of that I have already explained. So, then in this there are two types of air preheaters. One is a recuperator and the other one is a regenerator. This also I explained last time. Now, I am just giving you the background of this. Here recuperator is this, and this Ljungstrom air preheater. As I have already explained, this air preheater in the previous class, that it's a wheel, a wheel and a slowly rotating wheel here, and it's made of metal matrix, and the flue gas goes like this and goes away, and the air comes from the other side, and they are channelized differently. So, therefore, one half cycle. So, if you look at the cross section, this is a cross section shown and this is the thickness of the wheel, desiccant wheel. But what you do is, if you look at this cross section is shown. So, if you see half of this half is heated and this half is cooled by the air. So, it goes slowly. So, whatever heat transferred to the wheel by the flue gas is subsequently in the remaining half cycle it gives back to the air. So, therefore, that is why it is a regenerative. Regenerative means it stores for some period of time and then it is not immediately transferring the heat directly. So, therefore, it stores some part of this and then gives back in the other half of that. That is why it is a regenerative. Most of this desiccant is a desiccant type, even air conditioning also you must have seen this, it is a regenerative. Then air gas system. So, air gas system, air enters from the atmosphere by using forced draft fan, and there are air heaters, that is air preheaters, and then it goes to the burner. This is the one which is air side. Air is admitted into the furnace by considering the air come from the atmosphere and preheated and supplied to the burner. So, here there is a fan which is required, is a forced draft fan. The other side is the once they are burnt, it becomes flue gases plus air. So, the mass handled by the induced draft is much higher than the forced draft. The forced draft or drought, this forced draft means taking air and admit into the furnace a fan, but this fan handles low temperature fluid. That low temperature fluid means any, it is a compressor, say you are compressing that. Compressing low temperature fluid is easier than the compressing high temperature. That is why you have seen in a power plant, why do we need a condenser? Because after expansion we reject the heat and cool, so that pumping will be easier. Similar way here, the energy required for forced draft fan is less as compared to induced draft fan, which handles corrosive flue gas as at a higher temperature, and there is a possibility of leakage, and then this goes into the dust collectors where ESPs are there and then subsequently sent into the atmosphere through chimney. And this is called balanced draft. Last time I explained this, I am just repeating because to have a recap of the previous class. And the main objective of the draft is to supply to the furnace required quantities of air and for complete combustion of fuel. But then this is one part, that is air forced draft. But the induced draft is to remove the gases which are already generated in the atmosphere and send it into the atmosphere in a safer way, because it is an elevated portion. So, you have to I will explain you what is the importance of the stack or chimney, why we should send this into the atmosphere. The design of the chimney is also very important. In the previous class, I think I have told you that difference between chimney and stack, chimney and the tower. So, or if you see, there is we are going to discuss cooling tower, okay, cooling tower and a chimney. Then I will let you know what is the major. Chimneys are generally made of small aspect ratios, h by d, this is h, and this is the diameter of the chimney. So, there first is a forced draft which pushes the air into that, and induced draft which takes away from this one. So, there are different fans. Last time also I explained, one is a forced draft fan and induced draft fan, and sometimes one can also be enough. So, you can use one of them to overcome total air and gas pressure losses within the generator. So, but they are different configurations fans. I have shown here in the previous case also. The main forced draft fan is mainly used see what happens is your IC engines, no IC engines, you have seen IC engine. So, in IC engine air is taken from the atmosphere during suction. So, therefore, if you have these forced two drafts, which draft is better important? This induced draft is important, because we have to remove, if you have to use only one fan, you have to remove the flue gases out. So, therefore, you create suction in the furnace, so that the air automatically enters if you have to use one. But if in big plants we may have to use both here, forced and induced draft. So, what happens here if you have the IC engine case? Now, IC engines you have studied, no, you have already seen these cars, they are called naturally aspirated engines, and the other one is what is the other one? Turbo engines. So, turbo engines like having a forced draft. Okay. Natural means without only induced draft, that is the difference. Okay. So, if it is natural means if you create suction, automatically the air enters, it is that is a natural induced draft. Then apart from the induced, you have also forced, suction plus forced. So, here forced draft fan, as I have already told, I mentioned that generally it is used as mainly large steam generators, and practically in all marine applications. So, now of course, marine is not an important now, because most of these marine are earlier they are based on steam engines. So, they are placed at the entrance of the air to preheat and put entire systems up to the stack entrance under the positive pressure. When you push, it is a positive pressure, when you suck it, it is a negative pressure. So, these fans handle only cold air, which just now I mentioned. They have advantages which I have already mentioned also. It consumes less power, because it is a cold air, just now I mentioned, it is because low specific volumes in the air, that is why it is smaller one, and have lower maintenance problem, because you are pushing the air into the furnace. So, therefore, no maintenance, and their loads are reduced by the absence of additional gas equivalent of the fuel. That means, what is the meaning of this is the sizes of the induced, if when in a balanced draft, when the sizes of the forced draft is much smaller than the induced draft, because it has to handle large volumes, that is the meaning of this. And it is lower capital cost and operating cost also, because it is handled at cold. See, operating something in cold condition is different from the hot condition. So, therefore, its cold condition is always simpler. The disadvantage mainly here is because it is a pressurized. So, therefore, the pressure furnace is under pressurized condition. So, if you have a furnace like that, and then you push the air into that for combustion, some part is burnt, and it creates pressure, there is a possibility of leakages through the furnace, because it is a higher pressure than the atmosphere. So, this is what leakage is the major problem, because the gases pollutants, instead of going into the chimney, they may even leak through the furnace. Okay, that is a problem, that is the one. So, therefore, it has to be, the furnace needs to be airtight and withstand high pressure. So, that is why the cost will go up, that is the limitation of that, and special attention must be given to the design and inspection, because this is a furnace, and you have a water walls, everything, and it is burnt, and soot is formed onto the tubes, and then there is a possibility of tube failures and so on. In such case, what happens is, when there is a tube failure, people need to enter inside and they weld and then go, it is a massive thing. So, for that there are manholes to enter into that, and manholes have to be tight when it is a positive pressure, otherwise there is a leakage through manholes, that is the limitation of this one. Then induced draft is again, look, I have already explained, it is in the gas stream at the preheater and the stack in between that, This can be either before or after the dust collector, any location we can place it depending upon the configuration. So, it is essentially creates suction pressure, and entire place of the system is under negative pressure gauge. So, it has to handle hot gases and plus original air and the gas equivalent of the fuel added into that. So, there is a leakages into the system. There is a, see here you have problem here is when you force this, there is a possibility of leakage. Then there is a suction, if you are creating suction here, what happens, the atmospheric air enter also inside, there is a either way problem. So, that is a problem here, but the power required for this is very high as compared to forced draft, and then this induced draft fan should handle highly corrosive like all pollutants. So, therefore, the blades have to be made such a way that it is they can withstand pollutants as well as the gas ash pitting is also happen, because ash contains finer dust particle with a high velocity, it may hit the blades and then there is a possibility of fitting. So, therefore, the ID fans are seldomly used alone, that means suction fans are used only very rarely, because most of the time there is a combination of both. So, then if you look at the fans here, now I go directly here, you can see forward, flat, backward. You can see that there how the impeller profiles, blade profiles are there here. You can see the low speed fans with flat, this one is used for dust and corrosive gases. Yeah. So, then if you have generally these centrifugal fans with the backward curvature blading are used for FD, and forward is for ID fans. Okay. The forward is this is ID fan, this is FD. Okay. This is a forward backward curvature, this is forward, and this is straight flat here. So, lesser curvature results in lower tip speed and allows less dirt to the to clink to the back side of the blades. See here, the meaning of this is the curvature. If you have a curvature, what happens is when you use this rotation here, when you use this rotation, there is a possibility of ash agglomeration over the blade. So, therefore, that is another important thing here you should remember. So, generally you remember that ID fans are used for with a backward forward, and this is with a backward FD, and this is used mainly for dust environment and corrosive gases where you have NOx and other things, and if your fuel is highly impure and where sulfur content is higher, because I mentioned earlier in the beginning that foreign coals have a high sulfur. So, that is a main high calorific value, but high sulfur. So, therefore, in such case you have to use this. Then next is the stack. We have designed stacks also, cooling towers earlier for big power plants. See, the cooling tower which I am going to discuss is a massive cooling tower which is about 204 meters tall, massive tall natural draft cooling tower. Some time back we designed and given to some of these high supercritical power plants. The purpose of the stack is two ways. One is at this is the stack you have seen it. See, if there is no stack, what happens is if you have this furnace and if the gases come out, then they will these gases go into the atmosphere at lower level, so that the ground level pollution will increase. So, the main objective of this is to increase the height of rejection of flue gases, so that these gases are dispersed into the atmosphere properly. So, the stack has two functions, and one is to assist the fan to overcome the pressure losses, the other one is to help the disperse the gas effluents into the atmosphere. See, one objective is sending the gas into the atmosphere like this. If they are sent at the lower level, it is a problem. So, we are sending, that is the main objective. Another objective is you have a tall, this is a tall so this is the tall, suppose assume that there is no stack here, but then what happens is the you are sending the flue gases into the atmosphere at lower level. One is the pollution part, but forget about pollution part. The other one is what happens is the suction, that is a ID fan need to take out these gases and put into the atmosphere. So, if you put these flue gases at the lower level, because the atmospheric pressure is high, okay. So, therefore, you have to spend more energy, whereas if you put them into a lower atmospheric pressure, that means you have pressure driven thing, then you know that if you go higher altitude, the pressure reduces. So, then if you channelize this and put it at the higher altitude, what happens is this height creates a pressure drop, pressure difference. That pressure difference drives the flue gases to the up, so that the load on the ID fan reduces. So, that is the main objective of this to overcome the pressure losses which are due to the pipes and all, and this assists the fans. So, then if you look at how much pressure drop across the stack, and it is given by the density difference between the see here you have a stack here and the flue gases are entering here, and the height of the stack is h, okay, and the density of the flue gas is rho s, and the atmospheric air density is rho a. So, if you look at the pressure drop, driving pressure, because this once you put the flue gases into that, they try to move up because of the density, lower air density at the top. So, how do we calculate this driving pressure? Delta T across the stack is given by delta P d is equal to rho a minus rho s bar, that is average density. Here rho s is the stack flue gas density, and you have at the exit is different, at the entry is different. If you look at this average of the stack flue gas density is rho s bar, and you see this and you can find out the pressure drop, so that we can find out the assisted this one. So, then based on, if you replace the rho a and rho s by considering them as an ideal gas, both air and gas, so then you can replace this rho a by P a by RT, that P by RT, and same way P by RT per gas also. Then you can find out these here. See, the R value is incremental because flue gases and this. So, therefore, it also depends on the fuel. So, assume that it is the same, rho a is equal to rho s, sorry, R a is equal to R s. Then what we can rewrite is this P a by R a is equal to P a by R a into 1 by T a minus 1 by T s bar H g. So, generally you assume this temperature of stack average is assume that temperature of stack at the exit and temperature of the stack at entry, in and out, and you take average of that. So, this is the average of that, and then substitute that and find out what is the pressure driving pressure in the stack. That is a simple equation. So, you can find out this one. Then dispersion side, you can second important function of this is the first important, this driving force pushes the air to that, so that the load on the ID fan reduces, that is the important thing. Apart from that, this another important function is to disperse the flue gases, because this dispersion of flue gases in a stack is a big subject, but I will give you quickly in this. This you can say the flue gases goes into the atmosphere, and it is lifted up. See, the physical stack height is h, and the flume rise, this is called plume rise height, flume rise height is delta H, because the physical height is fixed always. This will be some couple of 100 meters, maybe 100 to 200 meters depending upon the location, but the physical flume rise height, the gases goes up into the atmosphere. Why? Because of its temperature. Buoyancy plays an important role, and apart from that the momentum. Buoyancy is the temperature dependent, momentum is the velocity of the flue gas. Velocity of the flue gas depends on the how you second, that is a ID fan. ID fan pushes the flue gases into the chimney. So, that velocity depends on that. How much it rises up above the chimney, it depends on the velocity of these. Not only velocity, but also the buoyancy, because the density is low. So, it tries to move up. So, the flue gas try to move up, okay, move up till the density of S is equal to density of air, atmospheric air. So, but what happens is that it can go up like that, but it is bending, no, this is bent like that. Why it bending? Because there is a wind velocity. So, this is the bending of this plume depends on the direction of the wind. So, because this it is again chimney design is a big thing. I am not discussing in detail, I will give you only brief, because you have in North Chennai we have power plants. If you go to the Chennai Ennore area, there are massive, some at least 5-6 power plants are there, and we have to study how the wind is coming into the city and going out of the city. We have sea breezes, land breezes. So, therefore, sometimes this flue gases can enter into the city and increase the pollution concentration also. So, therefore, it is bent and it is assumed to be a Gaussian distribution here, and as it goes further, the concentration of pollutants in the atmosphere reduces as it goes out. So, therefore, and it comes and touches the ground somewhere here, and where you have a higher concentration here. So, we have to find out what is the effective height of the, because the physical height, this H is fixed, but the delta H depends on various other parameters, how wind velocity is there. If there is no wind velocity, it will go up, but if there is a wind, is a turbulent wind, it may push this wind very close to the plume, very close to the power plant, and then this area will get polluted. So, therefore, there are many other factors, but we need to find out what is the delta H. This delta H is important, and this delta H can be found by various correlations. This is a Carson and Moses correlation, which is given by V. This is the equation here, important factor Vs. Vs is this is velocity of stack gas, okay, and then you have this is moving here, and then there is a velocity of wind. So, depending upon this, if wind velocity is high, then it will bend the other side. Apart from that, what rate the flue gases are going, and what is the diameter of the stack. So, now you can see d is the diameter, the Vw is the wind velocity, q is the discharge, that is the amount of heat which is discharged into the atmosphere, that can be found this mCp Ts minus Ta, that is Tas is the temperature of the flue gas at the stack, S means stack, okay, and A is the ambient. So, you can find out this emission rate, heat of emission is substituted here, and you will get the equation here, and specific heat you can consider is almost equal to the air 1.005 kilojoules per kg of enough dry air of temperature. So, this correlation is applicable to all atmospheric stability. Stability is atmospheric stability, what is that?
Smoke from the stack spreads in a certain way, it is unstable
Where did you study? Oh, so in that you studied, okay. So there what happens is, see, if the gas, if you look at the atmospheric air, because some who did not attend that course, I am giving you background of that. So if you look at the atmospheric temperature, this is the surface here, land surface, and the temperature of the atmosphere decreases with the altitude, height, okay. Temperature decreases with the altitude. No, if you go to top, it so it goes till to the atmospheric layer, stratosphere. So you know that in the aircrafts, aeroplanes fly at 13 kilometers or 35,000 feet. There the temperature is about minus 50 degrees Celsius. Here if you say it is 30 degrees, so there is a huge temperature difference. So therefore the temperature of the atmosphere decreases with the sorry, this is not, this is the height, okay. So if you say this is a negative side here, this is a temperature negative side, and this side is a positive, this is height. So as the you go, temperature decreases with this. This is 30, and this is a positive side, right. This is a negative side, and it goes. But if you represent actually, so if you take, maybe I'll take this here. See the temperature, this is a height, and if temperature decreases with, this is a negative side, negative, this positive. So the temperature decreases with the increase in height, then it is called lapse rate. Then this is the temperature, there is no change in temperature with height, and there is a temperature increase with the height. So if temperature decreases with the height, then that is called lapse rate, and then this is called inversion if the temperature increases with the altitude. So when you have a stack like this, and if if the temperature decreases with the atmosphere, what happens, this tries to move up, okay. The flue gases may go up, but whereas if temperature is higher at the top but lower at the bottom, then this is the inversion, then they try to come down here in this case. So therefore the stability is important as far as the dispersion is concerned. So that is what I mentioned, is applicable all atmospheric, whether is a negative, this lapse rate, this is dt by dz with the altitude is a negative here, that is called lapse rate. If dt by dz is positive, dz means height, z is the height, T is the temperature, is positive, then this is the this region, inversion. So this is applicable for all atmospheric stability. The next one is this Briggs relations. This is given by this equation, delta H is equal to 114 C F to the power of 1 by 3 and VW. Here F is a buoyant heat flux. Buoyancy, as just now I mentioned, that the because of the density it moves up here, moves up to the atmosphere. So the buoyancy flux is given by this equation. I will G Vs d square Ts minus Ta by 4 Ta. Here this value C is the some relation is given, it is called dimensionless temperature gradient parameter, and it is given by actually this is dt by dz, okay. This is some correlation dt by dz. This is is called air potential temperature gradient, and per this is how many degrees of change of temperature with respect to altitude, that is in terms of meter. So for neutral stability, that means it is 0, there is no change in temperature. See, if you have, there is no temperature with the change in temperature with the altitude, then it is a neutral kind of thing. If there is a negative, that means if it decreases it is like this, if it increases it will be like this with the height. So, this is taken, values are taken for stability kind of thing. This d theta by delta theta by delta z is considered in the range of this. So, almost you have somewhere 10 degrees Celsius per kilometer to 13 degrees Celsius per kilometer, that is the variation in the altitude. So, you have seen just now I mentioned here 30 degrees, here minus 50. So, what is the total? It is about 80 degrees, correct. So, 80, what is the height here? About 10 to 12 kilometers. If you divide that 80 by this, then you will get about 8 degrees Celsius per kilometer. Okay, there is a variation as you go. If the temperature is lower, it tries to move up. So, this relations is that for Briggs correlation. There is another relation which is given by TVA model. These are mainly meant for finding out how the dispersion mainly to find out delta H. This delta H is equal to 173 F to this flux here. So, and e to the power of this is stability parameter delta T theta by delta z. So, this is a temperature variation, and this is the equation which is dependent on the flux, momentum flux or buoyancy flux by wind velocity. This model, this delta H, see it can, if you look at that the flume if you have a stack like that and flume goes like that, okay, then this can estimate up to 2 kilometers from the stack here. That is the one which I am trying to tell, this model, okay. And it may touch even to the ground because there are different flume distribution models which I am not discussing here, but do not worry about that, this is important here. So, there are several theories based on assumptions and based on the wake of based on 3D Gaussian distribution and so on, but do not worry about all this. Some of these you try to remember and try to find out that. The next one is the steam generators, but steam generator is evaporator. So, it has different control systems as well as there are two types of components. One is called accessories, the other one is called mountings. Mountings are mainly meant for safety things, accessories are meant for performance improvement. So, mountings and accessories are performance, it improves the efficiency, whereas mountings are meant for safety, because see attemperator, I have mentioned one earlier, attemperation means to reduce the highest temperature of the cycle, I have shown earlier. So, attemperator is a mounting because it is meant for safety purpose like that. So, if you look at steam generator controls involves instrumentation, data processing and controls for various parameters like combustion, steam flow, temperature, pressure, drum level, burner sequencing, desulfurization, precipitation, precipitator and ash handling, system integration, startup and shutdown and automation. All these are the controls which are used for operating effective generation, okay, generation of steam. So, steam generator combustion means see what happens is, I told you in the previous case attemperation, no, see here combustion is In fact, recently I think last week this BHEL, I want to tell you this thing. BHEL people have come to me, what they wanted to do is most of these power plants, in it is a single grid, entire one nation one grid. So what happens when the grid level comes down, when the demand comes down, demand supply I explained. If demands come down, what they have to do? There are a lot of plants are producing energy, but all of a sudden the demand comes down. What you have to do? You have to reduce the input, reduce the load, reduce the generation. So most of these power plants at the off peak, mainly daytime, off peak time, when the solar generation is high, because solar you cannot produce in the night, whereas thermal power plants you can produce any time. So what happens is during the daytime the load is coming down. When the load comes down, these power plants have to be operated at part load operation, part load. So if you have a power plant consists of mainly two important things. One is the boiler side, the other side is turbine. The turbine, if you have a turbine of 500 megawatts, okay, you can operate turbine is like a engine, okay, you have an engine, okay, you can operate this engine ideal conditions to peak load, okay. Ideal condition to peak load means if you have a car, when you start it, it works, okay, there is no load on that, but as soon as you apply the load, change the gear, the load, and load can be anything, full load to high, this one. The turbine can be operated any part load conditions, any part load conditions. That means you can operate at 10, not literally 10, maybe 20 megawatts also, 500 megawatt you can operate 20 megawatts also, okay, you run that. But this heat which is coming from the boiler here, this is a boiler. Boiler, see if this is 500 megawatts, boiler should produce about 3 times the heat, about 1500 megawatt of thermal heat it should produce. Suppose if this load comes to 20 megawatts, 500 to 20 megawatt, that means what is a 500 to 20 megawatts means about how much percentage? So you have about 4%, okay, you are operating at 4% this, but you cannot operate if 4% of this is about 60 megawatts, okay. So you cannot operate boiler at 60 megawatts, turbine you can run it, but boiler, because boiler is, it has its own inertia, you cannot keep up and do that. So there some of these power plants, especially including power plant, I have seen one Hindujas and all these, they are operating very part load condition, becomes very inefficient way of operation. So these people are coming up, why don't we, when this load comes down, but we still keep the boiler at the same location, same condition, and what will you do, the extra heat which is produced, okay. So they have, then why don't we divert this extra heat into a energy storage, thermal energy storage, and whenever you need it, you take it back. So now they have come to me for designing a minimum, they want to install in one of those power plants, NTPC power plants, that at least minimum 2 megawatt to 5 megawatt hours of heat in the form of thermal heat storage. So that is a important thing. So now why I am telling this, because the combustion control is difficult, because we cannot, as I mentioned, if you reduce to 4% of the boiler, the combustion cannot work. So you cannot control the fuel flow rate, because the out of 1500, if you operate at 60, it's highly subcritical. So therefore it does not work. So therefore the controls, even if it is a part load condition, combustion control means supply less fuel and less oil, like lean type of thing. Then you have a steam flow. So when steam flows, then how to control the flow rates, temperature and pressure we need to control. Temperature controlled by that attemperation, and pressure you have to reduce the pressure. Then drum level means the water so you have a drum here and there is a downcomer, and in a normal case, and the risers are connected like that, and as I mentioned that the water liquid should be 50% of that. There is a called glass, half glass drum level indicator. So therefore this is a what liquid and this is a gas. Okay. So this, if this becomes like this, some 80% of the drum is covered with steam and rest is liquid, and the pressure may build up and it may explode. So therefore we have to keep always the drum level is 50%. So therefore there should be some controller here. Then other one is a burner sequencing, which burner, because I told you that this is a furnace, it has a several, I think in one of those I have seen about 8 levels of burner, one level here, next, and this tangential burning. Okay. So which one should start first, second, like that, that is a sequencing. And then ash handling, desulfurization per precipitator, system integration, all these controls are important for the boiler. So before that we will look at the feed water and drum level controls. Here feed water is this is a drum here. So this, there is a control valve which admits the water into the liquid into the steam, and this is connected by various controlled by control system, and which consists of various things, that is a drum level sensor and feed water flow sensor and steam flow sensor. All these are connected here, and they are so there is a trimming signal which controls the flow based on this steam, and this is the water level. Okay. So as I mentioned that earlier they used to connect with a glass tube, and you can see the glass wherever this is there, it can be seen. This should be half glass. Half glass means it should be 50% of the drum, and it goes below, you admit the water into that, like that. So this is the common I have mentioned, half a glass means that is the meaning of that, it should be 50% of that. Another important controls are pressure, steam pressure controls. This steam pressure control system mainly called boiler master. Boiler master means it controls the everything and maintains the steam pressure by adjusting fuel and combustion air flows to meet the desired pressure. Just now I mentioned here, if you reduce the sometimes how do you there is a I think I will explain you later, you send fuel and air, but it is burning here, but if you want to reduce the combustion level, instead of air you circulate the flue gas. Okay, take the flue gas which is going out and put it back, what will happen? The combustion level comes down, so that the overall input to the boiler comes down. This is called gas recirculation. Gas recirculation means if you put air, you will have a better combustion. So if you put gas, it is already flue gas, so combustion efficiency, that is called, is all these control methods here. So steam pressure sensors are directly on fuel and airflow controls. Of course they are either could this pulverized coal, and then FD fans, they are things which are connected, and different trimming signals from the fuel air sensors to maintain a proper air fuel ratio. And the control systems is very important. There are 3 desirable characteristics of control systems. All these controls, say you take any control system in the this one, 3 desirable. See, one is this is what you have set this, and most of these control systems are based on which control, most efficient one? PID, you studied these PIDs, isn't it? So it is based on PIDs. So then what happens is, the desirable characteristic is sorry Okay. What is the meaning of this? This, it should be stable, it should be stable, and it should be accurate, and it should be fast. Stable, accurate, fast, because it should reach stability, because it should not overshoot and go away from that. Okay. Then second thing is it should be accurate, close whatever this set, if it gives like this higher value, it's though it's become stable, but it never reach to the accurate value, it will go just fluctuate, and infinite time it takes to reach. Another thing is stable, accurate and fast. Okay. It should be stable, accurate and fast, because we study control system mainly. If you look at power plant, when the load increases, if you have a power plant, you are drawing more current, the frequency of turbine will come down. Okay. Frequency of generator comes down. When frequency comes down, if you draw more, what happens is there is a reverse flow from the grid, and there what happens, this generator windings will go off, then it is called blackout. So, there is a possibility of blackout. So, if there is a load coming, immediately it should cut off. The response is in this 5-second limit. So, the control system should be very fast, accurate and stable. And this is the one you can see here, trimming circuit for different thing, and of course, this is a pulverizer, all signals need to be there, but most important control is the PID control. They are now of course, there are modern control systems all there, but all are them are based on PID only. Then another one is the temperature control, which I have already mentioned, but again I am repeating this. The temperature may fluctuate because of the built up of slag and ash on the heat transfer surfaces. The ash agglomeration on the tubes may happen, and because of that there is an inertia of the heat transfer. So, therefore, the temperature either may go up or come down, because as the load increases, you have to increase the steam flows. So, therefore, the main two functions of this temperature control because of the load change is this mainly in radiant superheater. Radiant we have studied, inverted, radiant and all this configuration in the previous classes. The radiant superheater and reheaters have a drooping temperature loads characteristics, and which again whereas this convective type is has a rising temperature loads. Here I have given here, this is a convective and this is a radiative with the steam flows. So, therefore, if you combine, it will be like that. So, therefore, radiant and convective superheaters they have to be arranged in series to yield relatively final steam temperature over the wide range. So, because these two superheaters need to be operated tandemly such a way that your combined load will be almost flat. You have discussed, because I hope if this superheaters thing you have seen here, this is a radiant type and this convective type. So, that you have seen, one is parallel, that is U shape here like this, and then this shape. I think you remember that, which I have explained earlier. The next thing is how to reduce the steam temperature. This is what attemperation, separately fired superheater, gas recirculation. Just now I mentioned gas recirculation. What happens is, how do we control temperature of the steam from the steam drum? These are the risers, this is a downcomer. How to control this temperature? The temperature can be controlled by injecting some extra water into that, called attemperation, or otherwise you can operate a superheater. After this steam goes to the superheater, and this superheater is fired separately, and the evaporator is fired separately. That means you should have you have another burner set here. but it is very difficult to have that. Then otherwise to reduce, you bring this gas which is going back to this instead of air and fuel, that is called gas recirculation. If this temperature the plant efficiency, if there is a reduction of temperature by 30 to 40%, there is a 1% heat performance reduction happens in this. So, therefore, it is important to have different control systems to adjust the temperature. The attemperation device, how it looks like, it is like this attemperator, because we have to inject the water into steam. This is the flow going steam flow. I will explain you these things later, but now first you look at, see the attemperature, there are two methods. One is surface attemperator, then the spray or direct contact attemperators, and in surface attemperator you have shell type and drum type. And if you look at here, this is the steam with a mass flow rate is going here inside, and then if the temperature goes up, then you put this injection into this. So, therefore, the temperature comes down and there is a thermal sleeve, and it is like a Venturi type of mixing where the steam and the liquid are mixed here. This is called, this part is called attemperator. The other one is the temperature control. How do we control temperature? Because the temperature tries to move up like that. Okay. So, this is the steam temperature versus load in percentage. As the load increases, you have to supply the fuel and the temperature goes up. So, what happens here is we have to cut here by control. See, we should not allow to go further here. This is the design temperature, that is a wet at expansion temperature, maximum temperature of the cycle. So, this part has to be controlled. So, therefore, you have to, as soon as it reaches, as soon as the temperature reaches here, supply the water here, supply the water, that is one attemperation, that is a, see, cooling here, this one. But another thing is this part is a, after this level you go for gas recirculation, this is a gas recirculation. So, after that what happens, it raises here and goes like that flat, there is no increase in temperature. This is for with a attemperator, this is a gas recirculation. The another important thing is, I hope you understood all the controls. So, now another important component is the this is the heat supplied Q1, this is a heat rejected Q2. So far all the controls which we discussed, components are discussed with respect to this, okay, heat addition. We are not discussing turbine side and pump side components, because I assume that you know all this. Only now next part is this cooling side. How do we reject heat and recover heat, that is important. Okay. So, that is called cooling circulating water system, which is mainly circulating water, means here how to reject Q2, okay, that is done in cooling towers. You have to reject heat into the atmosphere. How do you reject? Either you send it into the atmosphere or send it into the water bodies. Okay, most of these coastal power plants, what we do, there is a sink, no, sink is required. Sink can be atmosphere or sink can be water body. So, if you look at our North Chennai thermal power plants, the nearest sink is sea, you dump into the sea. But what happens if you dump into the sea? If you high heat Q2, if you dump into the city, what will happen? There will be an ecological problem or environmental problem, because the marine system, marine life will get disturbed, fish and all these will die. So, therefore, you cannot send water that heat directly into the thermal pollution, we call thermal pollution. So, we cannot send that into the water body directly. What they generally there is a delta T of 5 to 8 degrees, I think. You cannot go send water 8 degrees above the temperature of this. Then what happens is, what will you do with the, because you know what is the water temperature, the exhaust of the turbine temperature is somewhere you have 100 200 degrees Celsius. Okay, that heat you cannot reject heat into the atmosphere. So, therefore, what you do is you send high mass flow rates of the cooling water here, and then cool it, some part you reject into the atmosphere, rest you to the water body. But in case of this is where you have a water bodies like sea or a river or something. But if you have a power plant in Jodhpur or mainly inland where you do not have water bodies to reject, then obviously you have to go for atmosphere, only air, you have to reject this air into the atmosphere, heat into the atmosphere by cooling circuit. So, we are going to discuss that this cooling part. This is first we will discuss how the closed feed water heaters look like. It is a heat exchanger we discussed in the cycle analysis. There are closed feed water heaters and open feed water heaters. Closed feed water heaters are in any plant, most of them are closed feed water heaters, only there will be one open feed water heater which is a deaerator that we discussed. And if you have a high pressure, this is like you see that this is a heat exchanger, you look at this, and it is a U type shell and tube type. This is a 2 pass, no, this is a shell, this is a tube type, and this is shell. So, it is a, the feed water enters here, there is a this is a manifold, it enters here, it goes into the tubes, and then it goes out here. Whereas this is the water which is here, and whereas steam is going like this. So, where it is used, you have a cycle. See, there is a, I have given one problem. You assume that there is a blade steam is taken here and cooled here, and then it comes here, it goes like that, and this is the heat addition. This is the feed water heater. I am assuming this is a closed feed water heater. So, or it can be, this is pumped forward, you can also put it back here, backward also. So, in such case this cooling water goes like this through the tubes, whereas steam comes from here, okay, steam comes here, and this is a steam, you can say steam inlet. So, then what happens is there are drains, there can be many drains. What happens is drain means, suppose you have taken here and then another one here, and then it comes here and further it goes like that. So, therefore, if you have a heat exchanger, this is the drain which is coming here and then further going. So, one drain inlet is this and drain outlet is here, you can see, you cannot see this is a drain outlet, but you can, it is a horizontal, it's like drain comes here and goes like that, out is like that. But apart from one drain inlet, but the drain can come from another feed water heater also. This is the drains inlet, this again also comes here into this from the previous one, and this goes out. There are several of these. You can have the vertical also. In high pressure you have 3 zones, here we call subcooling zone and condensing zone and desuperheating zone. So, the feed water temperature picks up here, whereas the steam temperature first is a superheated temp. This is a desuperheating, this is a condensing part, and this is a subcooling part. So, this desuperheating means the fluid comes reduces the temperature and then condense and then subcooled here. So, that is the thing. Whereas the feed water heater goes feed water heater is from this side. So, feed water heater goes the other side, the temperature goes up to this. Then the heat transfer, because here you have to look at how this heat is transferred to this working fluid. This is a hot fluid, this is a cold fluid, and you have seen the temperature differences are here minimum and here minimum, but you have maximum temperature difference, here maximum temperature difference. Okay, the pinch point we discussed in the previous time. So, then here how do we transfer heat, how do we find out heat transfer, because the area required, this area, surface area required by this can be given by Q by U delta Tm, that is the mean temperature. Q is the heat load, how much heat is transferred. See, this is the heat Q transferred from 1 this 1 to 2 to 5 to 8, whatever heat transferred from last 1 to 4 is equal to 5 to 8. Okay. So, the heat by how much, what is the average temperature and what is the heat transfer coefficient, because it is a shell and tube, and it consists of, if you have a, this is the tube where tube through the feed water is going and steam is getting condensed on the surface, because shell side. So, shell side is steam and tube side is the feed water. So, then you have to find out what is the heat transfer coefficient, both H out and H in, because of the flow conditions. So, these are H naught, Hi, HO, HIR, the heat transfer coefficients in the in this side. So, but this is the area which you can find out while designing the feed water heater. These are all closed feed water heaters. In closed feed water heaters, I do not know whether you have seen or not, in the previous when we discussed feed water heaters. See, this is a high pressure feed water heater. If you go for low pressure feed water heaters, low pressure feed water heaters, if you take, this is a high pressure feed water, this is high pressure feed water heater, HFW, high pressure feed water heater, whereas this is a low pressure feed. Low pressure means the steam entering in the feed water heater is at saturated condition, whereas this is superheated. So, therefore, superheated, you are taking steam from the turbine. If you take a turbine here, if you take this turbine, you can take blade steam here, blade steam anywhere. If you take here this steam, it is a high pressure and high superheated condition. So, this, if you, by the moment it goes at the end, by that time the temperature drops. So, therefore, for low pressure feed water heaters, this part may not be there, only from here saturation condition to this. So, therefore, their configurations are different. So, therefore, now going to the open feed water heater, as I mentioned, one open feed water in entire power plant cycle. I am not going to discuss this one because this is I am explaining on during discussion. So, this is only text, anyhow this will be given to you. This is a deaerator, open feed water heater is a deaerator. There are several different types of deaerators, and why the objective of deaerator is to remove the non-condensable gases. If the gases are produced during the circulation, those need to be regularly removed, and that is the main. And there are different types of deaerators for mainly different scales. You have a spray type deaerator, tray type deaerator, and combination of spray and this one. All these I have already mentioned, this concentration and all these are important. So, how do you deaerate? deaerate means remove the gases from the chamber. So, therefore, there should be some pump to remove, no, ejector side. So, you have to remove continuously. Generally, in condenser also you have a condenser. Condenser means it condenses the steam which is coming from the turbine. So, but it is at a low pressure, because we have to match to the heat rejection should be matched to the atmospheric temperature. So, therefore, atmosphere saturation temperature of atmospheric condition, so if you match, then the pressure of the, it is a suction pressure in the condenser. So, but how do you generate suction? That is every time you have to create suction. No? Suction can be batch process or continuous process. Essentially, it is a batch. Well, the meaning of that is, suppose if this room is there, you have to create suction in order to condense, but then after condensing some mass, then the suction will become positive. So, therefore, you have to continuously create low pressure in this. Then there need to be some kind of arrangement, mechanical device, that is ejector pumps are required. It can be a spray type or tray type deaerators or combination of this. It looks like this here. So, spray type is here, you can see it is a complex system, do not worry. Here you see, you can see that this is the condensate inlet here. You have seen how deaerators are. Deaerators means maybe I can draw the cycle, and if you have a turbine here, and this is the boiler, sorry, this is the steam and this is the boiler. So, you have, then some part is taken here and put it into the high pressure, this one, and then you have a low pressure, and then you have a condenser here, comes back. So, this is taken and put it here in this, and then this also put it here, and you have a pump here in the previous case. This is all the streams come there, and you reject this. There are, so all of them come in this way. Here you see the spray nozzles, distributing pans, then you have a spray hood, and all this deaeration tray, all this will be there, and there is a all the bleed steam. See, this bleed streams come inside here, and then they mix here, and then you have 2 stage, and the water goes here, and from here it is pumped. So, there will be spray nozzles to maintain the high pressure this thing, and so subsequently it is taken out here from the these vents, atmospheric vents are there, they will take out the non-condensable gases, go out. The circulating system, circulating water is mainly, it involves working principle, designs, selection of and practices. Mainly circulating fluid means the heat rejection, that is the from turbine, this circulation system. So, I will discuss what is the circulation system. Circulation system mainly for water is used for heat rejection. Because I do not want to go back, that is why I am drawing very roughly, please try to bear with me, because otherwise I have to go back to the. So, this Q2 is important, just now I mentioned, and what is the Q2? This is Q1 and W. So, the heat rejection Q2, you know that efficiency is equal to Q1 minus Q2 by Q1. Okay. We want to find out what is Q2. So, the Q2, or there is a QR, heat rejection, this the efficiency is in the order of 30%. Okay. What is the meaning of that? 60% or more than 60 to 70% is rejected in the form of heat. So, therefore, you see that this is the Q2 is Q2 is equal to 3 W. Okay. That means almost 3 times the 1.5 to 3 times the work. So, the work conversion is a smaller fraction, rejection is large. So, you have seen if you consider 500 megawatt boiler, 500 megawatt power plant requires 1500 megawatts of boiler, because if you take 30%. And boiler, you can see that it is a massive size boiler. I don't know if you go to any power plant, that boiler is bigger. You are adding heat in boiler of 1500 megawatts, but the other side you are rejecting 2/3 of the heat into the atmosphere. So, therefore, you should need a big device to reject also. Okay. That is also important in order to achieve this 30%. So, whatever how you reject heat into the atmosphere comes under circulating water system. Okay. How do we reject this? What this part is called circulating water. And how do you reject? See, this is a closed loop system. It is a closed, no, water is it is a closed loop. So, cycle is in a cyclic. But then this heat you have to take out, then use again design a heat exchanger, that is a condenser, where you supply cold water and remove this once it picks up the heat and you send out. And if you, for example, you send 1 kg of steam you need to condense, you have to spend large number of water to recover this heat at low temperature. It is a MCP delta T, that is all. This is a not big thing, but the meaning of this is Q, the heat can be at higher temperature. Suppose if I will tell you 5 kilowatt of heat at 1000 degrees Celsius. Same 5 kilowatt of heat can be at 50 degrees Celsius. Okay. The same heat can be at 50 degrees, heat is same, but temperature is different. So, now for example, 5 kilowatt of heat in the form of steam at 1000 degrees is assuming that it cannot go 1000, but assuming that it go at some fluid at 1000 degrees it is given. Same 5 kilowatt you have to transfer at 50 degrees, you have to send large mass flow rates, that is the meaning of that. Okay. So, 1 kg condense you have to send some hundreds of liters of fluid or kgs of fluid to recover at 50 degrees. So, therefore, why we have to do that? You cannot afford to take the heat at the same temperature and reject into the atmosphere. I just now told you water bodies, thermal shocks will happen. So, therefore, you send huge amount of when you go, I do not know how many of you, if you travel towards north by train, you can see these Ennore thermal power plants, lot of water coming out. You have seen that is a cooling water which comes out into the next time when you travel by train, if you can see that in the north side, which trains goes to Vijayawada or even Delhi, at the entry of Chennai, you can see that there are a lot of industries and big water coming out. That is a condensing water thing. Okay. So, this heat rejection is very high, that is why we have to design this one. There are different types of circulating water systems. One is a once through system, closed loop system, and combination of this. See, why I am explaining the gist of summary of this is just now I told you that you need to send huge amount of mass of water to recover some part of the heat rejected by the power plant. That you circulate water, because the pipelines, the cooling water pump is very massive, because they are large volume pumps, and you are taking heat and then rejecting into the water body at the delta T phi is equal to 5 or 80 degrees. But if it is inland means, for example, you have a power plant in Rajasthan, Jodhpur, where there is no water. See, again our in IIT also all air conditioning systems, we have a water problem. That is why most of these cooling towers are dry cooling towers. There is no wet, no adding of water into that, only reject into the atmosphere, where you do not have water. Water is, see, 2/3 of heat rejection, you need enormous amount of water, and if you go to the dry areas where you do not have water at all, then in such case you have to reject into the atmosphere, air. Okay. So, therefore, you need different types of circulating systems here, mainly when you want to reject heat. Then there are dry type of, that is these different cooling loops, but anyhow I will explain you this, because we have to design mainly for solar power plants, where in Rajasthan there you do not have water. There is a power, as I mentioned earlier, there is a 125 megawatt power plant in Pokhran, Rajasthan. There is a small lake, but that lake is only water is used for makeup water, not the heat rejection. Okay. So, even steam is heated and then expanded in the turbine, comes back condensed. In the process, these in open feed water heater, we are rejecting some mass of that. That means there is a loss of water every time. When there is a small loss of water, you have to add, that is called makeup water. So, the circulating fluid is, there are different types of circulating mechanisms. I think once through closed loop combination of these systems. We will discuss these in the next class. I will stop here, we will discuss in the next class.